Hi everyone, welcome for today's class. Today we will be doing the third lesson of electromagnetic induction. In the last lesson, we discussed Faraday's laws of electromagnetic induction, Lenz's law, and motional EMF. Today we will be discussing a new concept called self-induction. See the word self-induction. It takes place in a coil. Okay. You know how induced EMF is produced. Whenever the magnetic flux linked with a coil or a circuit changes, current is induced or EMF is induced. Okay. So if magnetic flux linked with a coil or circuit changes, an opposing EMF is induced in the same coil. This phenomenon is known as self-induction. Okay. So you consider a coil. This is a coil. Okay. When magnetic flux through this coil changes, an opposing EMF is induced in it. You know, induced EMF opposes the cause, that is Lenz's law, cause of production of induced EMF. Suppose you are connecting a battery to the coil and a key. Okay. When this key is closed, you can see current starts increasing. This increase of current will happen for a small time and become maximum. Okay. So during that time, current through the coil changes. So magnetic field inside the coil is changing. So magnetic flux inside the coil is also changing. As a result, an induced EMF is developed across the ends of the coils. And what this induced EMF do? It will oppose the growth of current. Here, increase of magnetic flux is due to the increase of current, growth of current. So, induced EMF opposes the growth of current. Okay. Similarly, if we open the circuit, current takes a very small time to decrease from maximum to zero. That time, magnetic flux through the coil is decreasing. At that time, due to the change of flux, induced EMF is developed in this coil. That induced EMF opposes the decrease of current. This phenomenon is known as self-induction. See, this is analogous to the inertia in mechanics. What is inertia? Inability to resistance to change the state of rest or uniform motion. Same thing. When current is increasing, the self-induction try to decrease it. When current is decreasing, the self-induced EMF try to increase it. Okay. This is actually analogous to the inertia in mechanics. So self-induction is the electrical analog of inertia. So there is an induced EMF developed in the coil when current through the coil changes. Okay. When current through the coil increases, induced EMF developed across the coil try to decrease the current. Similarly, when the current through the circuit decreases, induced EMF developed in the coil try to increase the current. Okay. This is the opposing nature of induced EMF, you know. This phenomenon is known as self-induction. So what is self-induction? It is the phenomenon of production of an induced EMF in a circuit or a coil when magnetic flux linked with it changes. Okay. Once the current becomes steady, there won't be no induced EMF. You know, for production of induced EMF, magnetic flux must change. Okay. Then we are going to define it. See, the magnetic flux linked with the coil, say phi, is proportional to the current through it, flowing through it. You know, flux is B into A, and B is mu 0 Ni. So magnetic flux is proportional to current. Current. And this magnetic flux is put a proportionality constant. That proportional constant I denote by L, Li. This L is known as, this constant L for this coil is known as coefficient of self-induction or self-inductance of the coil. Okay. So this self-inductance is the electrical analog of mass in mechanics. I told you self-induction is the analog of inertia. Inertia is a mass of measure of mass of the object. So self-inductance is the electrical analog of mass in mechanics. Okay. So that important point you have to remember. Now we can define self-inductance. Self-inductance L is equal to phi by I. So self-inductance is defined as the magnetic flux linked with the coil when unit current is flowing through it. Okay. That is a definition of self-inductance. Self-inductance is defined as the magnetic flux when unit current flowing through the circuit. The SI unit of magnetic flux is Henry. We denote by capital H. We can write one more equation for self-inductance. You know, induced EMF in the coil from Faraday's laws of electromagnetic induction d phi by dt minus d phi by dt. So minus of d by dt, what is phi? Li. Okay. So what you are getting? Minus L is a constant di by dt. Okay. So this is another equation for induced EMF minus L into di by dt in a coil. So we can find out L. L is equal to minus E divided by di by dt. So self-inductance, L is known as self-inductance, is defined as the induced EMF when current through the coil changes at the rate of 1 ampere per second. See, in this equation, when di by dt equals 1 ampere per second, di by dt, then L will be numerically equal to E. So L equals induced EMF when current through the coil changes at the rate of 1 ampere per second. So this is another definition of self-inductance. So self-inductance is defined as the induced EMF in a coil when current through it changes at the rate of 1 ampere per second. This is the definition for self-inductance. Now, what is a unit of self-inductance? Henry. We can define Henry using the same this equation. So I'm going to define Henry. See, you know the equation for induced EMF minus L into di by dt. What is L from here? E divided by di by dt. When E is 1 volt and di by dt equals 1 ampere per second. Self-inductance will be 1 Henry. So how will you define Henry? 1 Henry is the self-inductance of the coil if an EMF of 1 volt is induced across it when current through it changes at the rate of 1 ampere per second. This is the definition of Henry. 1 Henry is the self-inductance of a coil if an EMF of 1 volt is induced across its ends when the current through it changes at the rate of 1 ampere per second. So you have to remember the important point. Self-inductance is the electrical analog of inertia, mass, not mass. Self-induction is corresponding to inertia in mechanics. Self-inductance is the analog, electrical analog of mass in mechanics. Okay. Now, there is another phenomenon called mutual induction. We are coming to mutual induction. Next topic is mutual induction. See, the word mutual induction, there will be two coils. Okay. If current through one coil changes, induced EMF is developed in a neighboring coil. This is mutual induction. And the induced EMF try to decrease the change of flux in the first coil. Okay. So you are two friends. One is poor in studies, one is brighter in studies. The poor fellow may feel some jealousy, right? So what will happen when the clever fellow studies and getting good mark because of jealousy? That is the induced EMF in the poor guy. He tried to oppose his growth, right? This is mutual induction. As an example, just I am telling. Okay. So when one brighter student is studying very well and if he is scoring very high, the poor one, the poor coil, there is an EMF is induced in his mind. That induced EMF tried to oppose the growth of the clever coil, right? This phenomenon is mutual induction. See, this is one coil, another coil. Okay, when current through this coil changes, magnetic flux linked with the first coil change. Second coil is near to it only. They are not in contact. Then what happens? Flux with the second coil also changes, right? So there is an opposing induced EMF is developed in it. This induced EMF opposes the increase of flux in the first coil. This phenomenon is known as mutual induction. Okay, mutual induction is between two coils. So what is mutual induction? Whenever the magnetic flux linked with a coil changes, an opposing EMF is developed in a neighboring coil. Okay, the neighboring coil try to oppose the change whatever taking place in the first coil. This phenomenon is known as mutual induction. When the same opposing EMF induced in the same coil, we call it self-induction. Okay. So we can write this one, magnetic flux linked with the second coil and writing 5 to 1 proportional to current through the first coil. When current through the first coil is changing, a magnetic flux is developed in the second coil that is proportional to the current in the first coil, right? When the current through the first coil increases, flux will increase. Induced current is developed in the second coil. That induced EMF try to decrease the current in the first coil. This is mutual induction. So we can write 5 to 1 equals, put a proportionality constant, M21 into I1. M21 is the mutual inductance of second coil with respect to the first coil. Okay. Also, we can write induced EMF in the second coil is minus d5 by dt. So we can write minus d by dt of what is 5? M21 into I1. So we can take M21 constant di1 by dt. Similarly, you can define with respect to the second coil 512. What is 512? Induced EMF in the 512 is the magnetic flux linked with the first coil when current is through the second coil. So we can write M12 into I2. Okay. But this M12 and M21 will be equal. We can write equal to M. That we will prove later. M12 is equal to M21 is equal to M. They are equal. So we can define mutual inductance how? E is equal to minus d5 by dt. So we can write phi as mi d by dt of M into I. So we can write E is minus M into di by dt. So we can define M in this way. E is equal to E divided by di by dt numerically. Okay. So how we can define coefficient of mutual induction? It is the induced EMF when current through the neighboring coil changes at the rate of 1 ampere per second. If di by dt is 1 ampere per second, then what will be? M is equal to E numerically. So how will you define coefficient of mutual induction or mutual inductance? It is defined as the induced EMF in one coil when current through the neighboring coil changes at the rate of 1 ampere per second. Okay, dear all. Thank you for watching. Keep on watching. Subscribe my channel. Goodbye.